So I will just give it a few minutes. People are still checking in. There were some password issues. All right, I guess it's somewhat stable now. So we'll slowly get started. So good afternoon. My name is Niels Madsen. I'm a professor at Swansea University, and I run an experiment at CERN that has been mentioned previously in these webinars. It's a big research lab in Europe. I will introduce it briefly. So this is the last in this series of webinars. And as in the previous ones, you cannot use the chat function, but you can ask questions with the Q&A. And there will be a colleague here called James Bateman, who was also the other 2 days. He will help with answering questions if they are related to, well, also to physics, but in particular in terms of admissions. And then I'll try to answer questions related to my talk, to the presentation. So the presentation today will be in 2 parts. First, I'll give a presentation about the kind of physics we do, and with an introduction to CERN included. That comes natural as part of it. And then after that, there will be an opportunity to ask some questions about the physics on the talk. And then I'll follow up with a virtual tour. We'll probably not spend a long time on questions right after talk, and dive relatively quickly into the tour, where you're also free to ask questions. And of course, you're free to ask questions at the end as well. We'll keep going on until people sort of run out of steam, or we run out of steam. Okay, so I will get started on the presentation. Bear with me a second here. So thank you for joining today. I'll talk about antimatter at CERN and finish off with a virtual tour of the experiment. And we dive straight into it here. So the first question, of course, you may ask yourselves is, what is antimatter? Well, to introduce it briefly, I'll come to more details, of course, is that basically for more than half a century, so since 1930 to be more precise, physicists have believed that the universe is made of both matter and antimatter. Now, that doesn't explain anything at all, so let's go a little bit back in history to see the early days for how they come to believe that and what that actually means. Back in the 1920s, so almost, well, pretty much 100 years ago now, a famous physicist called Paul Dirac, he combined the nascent quantum mechanics, Schrödinger's equations, with Einstein's special relativity that you all heard about already 2 days ago from Simon. Because what he realized was, of course, that the initial Schrödinger equations that describe the very, very small, so what happens inside atoms specifically, did not include the fact that there's a speed limit in the universe. And that speed limit, for all reasonable assumptions, also had to apply inside atoms. So Dirac basically took that speed limit and applied it to atoms, to put it simply. And when he did that, lots of things popped out of the woodwork. And one of the things that popped out of the woodwork was that the particles they knew, which were not so many at the time, they had to have twins, if you want, of the same mass, but the opposite charge, opposite quantum numbers, but here we keep it simple, so we stick to charge today. Okay, they didn't know too many particles at the time. They'd heard of electrons and protons, right? So that's what we consider matter. That's what matter is made of. Neutrons were only discovered later. So antimatter in this concept would basically be a positive version of an electron, so an electron with a positive charge, which was quickly named a positron because it was discovered very briefly afterwards. But of course, the proton would also have an antiparticle that's then called an antiproton. Okay, Now, the positron got its own name because, as I mentioned, it was discovered very quickly. Dirac postulated this in 1929, approximately 1930, and it was discovered already in 1933, and the antiproton only about 20 years later. We'll return to why that might be the case. Now, of course, as soon as you can imagine that you have opposite charged particles, well, if you think about what keeps atoms together, it's the electrical force between the constituents, so the protons and the electrons in particular, keeps them together. So you can imagine if atoms are made of that we stick with the simple one, like the hydrogen atom, an electron is bound to a proton. Well, in principle, it should be possible to make a positron, an anti-electron, stuck to an antiproton, which would then be called antihydrogen. So this is what we normally term antimatter, as opposed to the constituents that are antiparticles. That's a bit of a technicality. Now, antihydrogen, on the other hand, as you might imagine, of course, required you to first discover the antiproton and the positron, but then a lot of work went into it. And only in 1995 was the first antihydrogen made at CERN. And the first low energy antihydrogen was only made in 2002. And I will come back to why that's important. Okay. So that's all very nice. You have these oppositely charged particles, but what's anti about them? Well, one thing that's anti about them is that if matter and antimatter meet, they annihilate. Okay, what does that mean? Well, that means that, for instance, if a positron and an electron meet, like in the cartoon you just saw, they will both vanish, and all their mass is converted into energy according to Einstein's famous equation, E = mc squared, so the mass times the speed of the light squared, that you see down in the lower right corner there. Okay, so I've described the release of all its energy as 2 photons here, so that's what the gammas and the arrows indicate. So 2 photons come out of this annihilation, and it's converting all the mass into energy according to this equation. You can think of this equation as an exchange rate. Okay, if you have some mass, you get quite a lot of energy because you multiply, and you can convert it all because you multiply the speed of light squared. Well, that sounds great. Okay, so, but how does this compare? And it also perhaps sounds rather exotic to some of you. Now, as it turns out, it's not actually particularly exotic. It's what nature does all the time, converting mass into energy, and to some extent vice versa. So a simple example is in chemistry. Like, think about it. Okay, chemistry, you burn something. Let's say you burn something. So it gets hot. Okay, where does the heat come from? You might wonder, well, it's some chemical reaction. Yeah, exactly. But what happens? Where does the energy come from? Heat is kinetic energy, effectively, right? It's movement. So where does that actually, what is it that goes away so that you can have heat? Well, what goes away is mass, even in chemistry, though it's very hard to measure. So this diagram now I brought up here shows the energy density in terms of energy in kilojoules per gram you get out if you apply one of these processes, right? So you can see on the very left, you have chemical processes, right? So here we've taken one of the most efficient chemical processes I could come up with, which is just basically mixing oxygen and hydrogen, which makes water, and which is what used to send rockets into space, mostly. Okay, and if you mix those two and you do that energy calculation, you get something like 10 kilojoules per gram out, which is enough to fire a rocket into space. And that goes on by mass conversion, right? E = mc squared. Now, something that's significantly more efficient is fission, which is the next one in line. Fission is, of course, splitting of nuclei. Here's the example of uranium-235. That's what this calculation is based on, but it's all in more or less the same ballpark. And you see immediately, this is a logarithmic scale for those who are not used to that. So each line is a factor of 10 more. Each horizontal line indicates an extra factor of 10. So you can see there are 7 more factors of 10 in fission and in chemical reactions, right? Which is why nuclear weapons are so powerful compared to traditional weapons that are chemical. Okay. So here you get about 10 to the 8 out. Now, fission requires you to have some heavy nuclei, which is not very common in space, where hydrogen is the most proliferating thing. So instead, in a star, stars run on fusion, which is the opposite process. Here's a calculation for deuterium-tritium fusion, which is what one hopes to use here on Earth eventually to produce energy. This is sort of roughly a factor of 10 more efficient than fission. So antimatter inscribes itself in this sort of, I don't know, categorization here as basically just being 100% efficient. So all the mass get converted into energy in principle. So another factor of 100 approximately. Okay, so it's very efficient. So if you have some antimatter, it's a really efficient way of storing energy if you want. You need, of course, for it to meet some matter to get it out, but matter there's plenty of, as it turns out. Now, that's great. So if I have some antimatter, how can I get energy out of it? I can get energy out of it, so I could use that to power my spaceship. This is what they do in Star Trek, for those of you who watch that. You can do sort of rough calculation, back of the envelope, and would maybe take about a ton of antimatter to go to Alpha Centauri and back. Alpha Centauri is the nearest star system, about 4 light years away, if I remember correctly. If you're less ambitious, you could try to blow up the Vatican. According to this movie, Angels and Demons, that will take about 1/4 of a gram. 1/4 of a gram is roughly like a small Hiroshima bomb. So that probably would blow up the Vatican. Now, fortunately for the Vatican and unfortunately for those who want to go to Alpha Centauri, this is not just unrealistic, it's pretty unattainable as it goes right now. First of all, you might imagine quite easily that there's not antimatter lying around here on the ground, because getting in contact with matter is easy. Lots of things around here are made of protons, neutrons, and electrons. So that means that at least as long as you stay here on Earth, you're going to have to make the antimatter yourself. Now it becomes a problem, because you have to do the opposite process, right? You have to convert not mass into energy, which turned out to be quite simple, some level at least, but you have to turn energy into mass. Now, of course, this is possible, but as with the Stone Age man, we don't have a lot of control over that process. So nature has decided what we actually get out if we have some energy. So here's just an example of a fundamental limit that comes into play. If you take protons and accelerate them up to a very high energy, which in this case is a momentum of 20 TeV/c, I'll come back to that, and then smack them into something, you can convert some of that kinetic energy. That's basically kinetic energy you're converting into mass, but you only get like 1 antiproton out for each 1,000,000 protons you shoot on your target. Now, what happens to the rest of the energy, you might wonder. Well, some of it goes into other particles that might come out. A lot of it just goes into the proton changing direction. So it's really not actually lost. It just doesn't really do anything useful for us. So it's already very, very hard. Now, another problem that they don't deal with in the Vatican movie, in the Angels and Demons movie, is that storage, you cannot store these guys. So in this movie, they have these antiprotons, presumably, they don't say that at any time, stored in a little vial that they carry around, or at least the evil protagonist carries around and stores in the Vatican somewhere. Now that's pretty unrealistic, because they say about 1/4 of a gram they have. Now, how do you keep charged particles? If this is antiproton, they're charged, they repel each other. How do you keep those stored? Well, it turns out that the most efficient way you can store a lot of particles at a very high density is using magnetic fields. And you need very strong magnetic fields. So even with the strongest magnetic fields that I could sort of realistically put in, 1 gram would take a volume of 10 to the 7 cubic meters. So we're sort of getting closer to cubic kilometers here. So certainly not something you can hide underneath the Vatican. So you'd be better off if you could make something neutral, like antihydrogen, as I just mentioned, if you could stick some positrons on it. Now, as we'll come back to, making antihydrogen is exceedingly difficult. Okay, and time consuming. So just from an energy perspective, it's difficult. So it would take, to make about 1 gram of that, it would take about the total world energy output for 50 million years. So that means everyone here should eat grass and certainly not be on webcasts for 50 million years. So try to get that through, at least in a democracy. Now, of course, we're not that efficient, as you will see in a minute. In fact, it would take 50,000 billion years to get this done. Okay. So we're not going to get antihydrogen or antimatter weapons anytime soon, unfortunately, for those who are dreaming of that. So why are we bothering? Well, what is the puzzle? Well, the puzzle is, at some level, this annihilation that I just mentioned. So, for instance, positron on electron is symmetric. What does that mean? It's like a mirror image. It means that if you manage to do the opposite process, let's say you manage to convert some energy in some way into antimatter, you get equal amounts of matter and antimatter, right? In the same way as you need a positron to meet an electron for this annihilation to happen, the opposite process, which is called pair production, produces them both. You could keep it simple and say, well, you can't make charge out of nothing. Okay, so I wouldn't be able to make a positron if I didn't make something negative, which then becomes an electron, because else the universe would end up in a big mess. Now, that doesn't seem like itself like a problem, except that as far as we understand, and there's lots of evidence pointing to this, the universe started with just energy. It was just hot, a very, very hot and also a very, very small place. This small hot moment was called the Big Bang. And at that time, there were no particles around. There was just photons, effectively. Okay, but eventually it cooled down and matter and antimatter appeared and should have been made from pure energy in equal quantities. Now, that's all very nice. Except that, of course, we don't have anything here on Earth. Now, that's not necessarily a problem, but certainly today there should then be equal amounts of matter and antimatter, but it turns out there's about this much, as far as we can tell, from cosmic background radiation and from all the stuff that the Earth is bombarded with. It seems that there's about no antimatter. There's no bulk antimatter. There are no antimatter planets or stars or something like that hidden in the universe, as far as we can tell. Okay, now, to put some number on this, to give you some feeling for where this is not a model, it's just to put a number on it. Okay, for every 1 billion particles of antimatter that was around, there was 1 billion and 1 particles of matter around. They all annihilated, and then there was just one left of matter, and that's what ended up becoming the universe that we see today. How do we know this? Well, we estimate this because we know the temperature of the universe today, and we believe that this temperature is a cooled down version of this original explosion, which was all the matter and antimatter annihilating, apart from that little bit that became what we have today. Now, this is not a model, this is just to give you some feeling for the numbers. In fact, as far as we know, well, certainly we don't have any model of how this came to pass. Now, this describes itself in a bigger picture of lots of things we don't know. So this is more talk of what we don't know than what we know today. And another way to look at this is to look at the energy budget of the universe. Okay, you might have seen this diagram before in some other context. So I have simplified a little bit the description here in 3 categories here. This is sort of, if you have all of the energy that's in the universe, that we could split it up in 3 categories. One we call the known stuff. So this is normal matter. This actually should technically include antimatter because we do know antimatter, at least at this level. Okay. Then we have the known unknowns, which is what we call dark matter normally. It's called known unknowns because it behaves gravitationally in a way we understand. So it's called dark matter. Okay, matter means that it behaves like matter. Okay, and the last, but the major bit is the unknown unknowns, which we call dark energy. Okay, basically for lack of a better name, because we don't know what it is or how it came about. Okay, now, so there's a lot of stuff we don't know out there. But the key thing here for this talk is that there doesn't seem to be any antimatter, right? It just seems to be missing. But our current model that does describe pretty much everything that happened in the universe, at least with a good approximation, predicts that half of the 5%, or at least, well, in fact, it doesn't predict anything about the dark matter and the other stuff, but the bit that we know about the universe, half of it should be antimatter. Okay, so there's a big mystery. So when you don't have a model, which we don't, we need to figure out if there's something wrong about antimatter. Now, we've been studying matter, of course, for hundreds of years. Antimatter is sort of a new kid on the block, at least since 1930s. So we need to look at it more carefully because there must be something we've missed somewhere. Okay, so we need to look more carefully. Now, what we can do in principle, and what people have, of course, done since the positron was discovered, is that we can look at antiparticles individually. Okay, the positron or the antiproton or other antiparticles. Okay, what I will focus on today mostly is to talk about antiatoms. They're interesting for a number of reasons I'll come into. In some way, you could say they're the only pure antimatter system we can make that is a bound state. Okay, so in some sense, if you're inside an antiatom, this is about the closest you can get to an anti-universe. Very small one and not quite a very good copy of one, but as close as we can anyway get. Now, we can only make antihydrogen. You will soon know why. So how does that help? Well, it's the only antimatter, pure antimatter system we can actually make so far. Okay. Now, it has a really big advantage in terms of looking carefully at something, is that it's neutral. What does that mean? It's electrically neutral. Okay, so it doesn't have any charge. Think about yourselves when you walk around on a carpet at home, for instance, and you pick up some charge and you can discharge it on your little brother or sister or someone else you want to annoy. Okay, so it's very easy to pick up charge. Okay, the same is true for physics experiment. It's very easy to pick up charge. So if something is neutral, it doesn't care, and it's much easier to do more precise measurements. Now, another really big advantage is when it's neutral is that you can actually potentially measure gravity on it. I'll come back to that a little bit. Okay, so we have a chance to measure gravity. Now, but what really pushed us into going for antihydrogen was that it's an atom. Okay, it's an antiatom, but it's a bound system with internal states. Okay, so we can use what's called spectroscopy to study it. Okay, atoms have these internal states that give rise to, for instance, them fluorescing at different colors, which is, for instance, why sodium lamps in the evening that are used, street lamps, often they're yellow, because sodium has a lot of yellow transitions that you can excite. And you can study these transitions in great detail. And we've known that atoms, or at least something, has transitions for almost 200 years now. On this graph I show here on the right, I only show the last 100 years. Okay, so you're going to have to live with that, because we only really started doing this carefully at about the time when we discovered atomic physics, if you want to be precise. Okay, so what this graph shows is a comparison. Well, it shows a hydrogen measurement of the first, from the ground state to the first excited state of hydrogen, and the history of how precisely it's been determined. Okay, and as you can see, what the exponent on the y-axis shows is basically the number of digits. So in the 1920s, they knew this to about 5 digits. And today we know this to almost 15 decimal places. Okay, so we can study these things very precisely. And the hope, of course, is that by bringing these techniques that now have matured for more than 100 years on the question of antimatter, we can unravel something undiscovered as something new that could hopefully give us keys as to how we move forward and understand what's going on and where half the universe went off. Now, just to put this in a little bit of a perspective, this may seem very far away from your daily lives, but in fact, you're all using spectroscopy every day in some indirect way, because you're all making use of the GPS system to find the bakery or whatever you want to find, track your running route or whatever you do, because the GPS system is based on atomic clocks, and spectroscopy of atomic transitions is what an atomic clock is. It is just a frequency. You measure a frequency when you do a spectroscopy on an atom, and a clock. What's a clock? A clock is something that ticks, that's the frequency, and something that counts. So a frequency and a counter, and then you have a clock. And that's basically what an atomic clock is. The atom gives the tick, and something else does the counting. Okay, the GPS is based on these satellites that basically tell you what time it is. That's the only signal your phone receives. It doesn't receive anything super sophisticated. It receives a signal from a satellite where the satellite keeps telling you what time it is at the moment the satellite sent the signal. And then in principle, you can calculate how far away the satellite is, and by knowing its orbit, which it does tell you once in a while, you can know where you are. Now, on this cartoon, you might believe, and reasonably so, assume that you would need 3 satellites to triangulate your position. But it turns out you need 4, because you don't know what time it is. You don't have an atomic clock in your phone, and then it would be a lot more expensive and a lot more bulky. So that's why you need 4 satellites at any given moment. Now, just to put this in perspective again, the world record in this kind of measurements, which in principle you could imagine applying to antimatter studies in the future, is 18 decimal places. Okay, if you started that clock at the beginning of the universe at the Big Bang, it would just be 1 second off today, right? It's like measuring the distance from the Earth to the Sun with 0.1 micron precision. It is the most precise tool in the human toolbox of all things. So of course, it's very attractive to be able to possibly bring that to antimatter and this riddle. But of course, as I said earlier, we don't actually have antimatter lying around on the ground here, fortunately for us, else we wouldn't be here. So we first have to make some antimatter. Now, how are we going to go about that? Well, positrons, anti-electrons, they're easy. That was why they discovered first, because they're quite light, right? The energy equivalent is 500,000 electron volts, so 511 kilo electron volts. So in fact, that's enough energy. That's the kind of energy that is in a radioactive decay, and specifically positrons are what we call beta plus decay. Okay, so that's easy. Now, antiprotons, like the proton, they are about 2,000 times more massive, so you need a lot of energy, right? Recall E equal mc squared. If you go 2,000 times up in energy, So you need about 2,000 times more energy, at least roughly, compared to a radioactive decay. Now, you don't get that in a radioactive decay, so you need something bigger, perhaps something that looks like this. And that's what we can't do in Swansea. So that's why we're not doing it in Swansea. So what do? We go to CERN in Switzerland. Okay, what is CERN? Well, here's a short video that shows you what it looks like. It looks like some industrial neighborhood pretty much anywhere, except you see the mountains in the background here, and the trams in the front and the countryside around it. So the site is what you see in the front. The big ball on the right is what they call the Globe of Innovation. It's an exhibition hall that you can see if you come and visit. Okay, that doesn't really explain what CERN is. Well, CERN, just to spell out the abbreviation, at least it means Conseil Européen pour la Recherche Nucléaire. Okay, it was founded in 1954, if I don't remember wrong. And what it means is it's the European Center for Nuclear Physics. Okay, nuclear research to be precise. Okay, it's just a French acronym. It's a worldwide collaboration, CERN, even though it has 23 member states. Those are the dark blue ones on this map. And then after that, I've forgotten what the color code is, well, more or less. Okay, it has 23 member states. So the member states are the one that actually run it. Okay, but there's more than 100 nationalities at CERN. There are institutes from more than 80 countries, because you do not have to be a member state to do physics at CERN. Specifically, member states, they contribute and they participate more in the knowledge development at CERN. The UK is a member state. And there's perhaps about 15,000 people involved. On a daily basis, maybe only about half of those are actually at CERN. Well, not right now because of the crisis. But it's about 15,000 people. Out of these, about 2,000 of them are CERN staff. One way to think about CERN in this context, sort of in terms of organization, to think about it as an airport. Okay, the staff are the people who make sure there is an airport, that there's tarmac, that there is fire rescue services, that there is security protocols and all that. And then the airlines are all the physicists or the research institutions that come and actually do the research. And they bring in and CERN delivers the particles, which in the airport jargon would be the passengers. Okay, so CERN is an infrastructure, international collaboration for doing physics, but in some sense it doesn't do it itself. It's all the other 13,000 people that does the physics, if you want, mostly. Okay, it has a budget to keep this running of about 1,000 million Swiss francs, so 1 billion Swiss francs a year, to give you some idea. What is it for? Well, it was started basically to avoid everyone running off to the US after the Second World War, all the scientists at least. Okay, and its sole purpose is to basically do fundamental physics. It started out, of course, being nuclear physics, which is why to call it nuclear. Nuclear physics is sort of covered, at least enough that it's no longer something CERN has to do. So now it's more particle physics. In some ways, you can argue that CERN is slowly going back in history. You can see this diagram here of the right, which is a physicist's view of the history of the universe. Okay, along the horizontal scale towards the right, you have the Big Bang on the left, and then you have the universe today on the right. And then it's a logarithmic scale again, so it goes very quickly. And as you can see on the very left, just before inflation, you just have photons. And then all of that started cooling down, and you started in the first sort of bigger ellipse where you have gluons and other kinds of particles, quarks and things flying around. Okay. So CERN is trying to study all these fundamental building blocks of nature to try to figure out how it's all put together. And that also, of course, also implies in some sense going back in time and basically study conditions that are similar to those in the Big Bang. That's what's sort of indicated by the insets above, where it says accelerators can get there, because it's a question of energy. Okay, E equal mc squared again. One of the things that CERN, of course, spends a lot of time on is the standard model, as it's called, of particle physics, and I'm sure some of you at least have heard of. We end up, currently, it's basically composed of these particles. The Higgs boson in the middle there was the most prominent one to be found not so many years ago, to be discovered. All of these particles make up what's around us. Mostly, of course, we're made of the leftmost row there, the up and the down quarks and electrons. That makes up protons and electrons and atoms. Most of the other particles are very short-lived and therefore we don't see them very often, but so you have to make them intentionally somewhere to have a chance to observe them, and that's what CERN does. Okay, the standard model, just for covering any holes, does not cover gravity. So the last 2 days you've talked about that specifically. Now, how do you study all this stuff? Well, let's go back to the basics again, the E equal mc squared. So what's the idea here? The idea here, you want to study these particles that don't normally hang around, so you have to make them. You basically, the only way you can make something is by using this equation. You have to convert some energy into matter and mass. So CERN has the LHC, which is currently the largest particle accelerator, the most powerful particle accelerator in the world. It's about 29 kilometers long circumference, and it's cooled down to about 2 degrees above absolute zero to actually work. Just to give you some idea of the amount of energy, it's actually surprisingly, even though it's smacking protons on protons, I'll come back to that a little bit in a second, it's the actual energy in the beam is actually enormous in itself, because there's so many protons at such a high energy that it's about a locomotive worth of kinetic energy. That's like a car. So a normal car is about 1 ton going at Mach 2. That's the kinetic energy of the fully energized beam. So that can shoot through anything, which is why it's 100 meters underground. And it was built by a famous Swansea student called Sir Lynn Evans, up from the valleys. Now, just to give you some idea of that scale, if the LHC was in Swansea, it would look like this, here centered on Singleton campus. Now, they didn't build it in Swansea for lots of historic reasons. I don't think it was even in the suggestions. Here it is on the background of the Geneva area in Switzerland, where you see the lake up on the right, and you see a little bit, it's hard to tell in this photograph, which is why I showed the video before, you see the mountains on the left. And you see the accelerators cartooned on top of this aerial photograph. So the LHC is, of course, the large one here, and it makes lots of antiprotons. But as it turns out, they're not too useful for us. So instead, we use this little one down here called the AD that we'll now look at in a little bit more detail. Okay, so just to get some idea, I mean, we still need the energy. That's why we're at CERN, but we apparently don't need the LHC. So how does this all go about? Well, the way you get energy to do this conversion of energy into mass is to accelerate some particle up to very high energy and smack it into something. In the LHC, they smack protons on protons, and protons are very easy to get. Basically, you take a gas bottle of hydrogen, as shown in the movie here, and you rip the electrons out by heating it up like crazy, or by having electrical discharges. So this little cartoon just shows basically that you have this so-called plasma duotron proton source. Basically, protons come out of that, and you rip them out with some electric fields, right? That's relatively easy to rip an electron off a hydrogen atom and then take the proton out. Okay, so they do that. Now, what does that mean? So then they have this big mess of accelerators that you see here on this map. Well, to orient yourselves, there's this flashing dot down here in something called LINAC 2, that's Linear Accelerator 2. It will be replaced from now on by LINAC 4. CERN is in shutdown mode right now, apart from because of the COVID-19. And basically, you now need to accelerate these protons. So you shoot them along. Here, they accelerated linear accelerator. That accelerates them up to some energy. Now, then at some point, you can't do much better with a linear accelerator. So you send them around in a circle. Here you need the booster, as you can see it from 1972. That brings them a little bit higher up. It's like changing gears on a car. Then when they're going far enough, you shoot them into the proton synchrotron, which is the basically more or less almost the original machine. You see it's from 1959. CERN was founded in 54. And then you accelerate them more. Now, normally you would then shoot them onto the SPS above there and into the LHC if you want to produce Higgs bosons, for instance, to get to the very highest energies. But at the time they leave the PS, they actually have enough energy to make antiprotons. So we shoot them over here to where you can see AD and Elena written, okay? And they smack into this place. And what happens there, they basically smack into a target, okay? Bah, a little piece of iridium. And out of that, some antiprotons come out. So this is where you smack 1 million protons on this target and you get 1 antiproton out. So in total, with all the protons being smacked on here, you get about 30 to 40 million antiprotons out of this. Now, why not do it on the LHC? That's because when they come out here, they still have a manageable energy. of about 3.5 times their rest mass. Okay, and you can select them out and shoot them into this machine, which is called the Antiproton decelerator, which is the one we're going to visit afterwards. You see the scale down at the bottom here. This is a relatively small machine for CERN. It's about 180 meters in circumference, and the particles come in on the top left, and then they're selected so that you select only antiprotons, and you send them into this machine. Because of course, what we want to do with these antiprotons is we want to study them very carefully. If you want to study something very carefully, it certainly helps that it's not moving along at the speed of light. So basically, we want to stop them. We want to bring them as much to a standstill as possible. Now, this machine doesn't quite do that. It brings them down to 10% the speed of light, which is still not nothing, but it is certainly something surmountable at this point. But you need this sort of machine to do that. So the antiprotons are shot into this machine every 2 minutes, and they're decelerated, and then they're shot out to all the experiments, which are indicated with the colored blobs. So I work on the experiment. Swansea is involved in the experiment called Alpha down here in the bottom right, sort of middle right. And that's the one we're going to visit afterwards in our little virtual tour. Okay, here's a quick photo just to get you some idea of what it looks like in there. You will see more of them later. And there is something else that's unique about this. So CERN is not the only place in the world where you have accelerators, but it is definitely the only place in the world where they make low-energy antiprotons. So our experiment is here, and everyone else in the world who wants to make antiprotons is pretty much also here. Well, they're all here. And you can see how they're proliferating around us, so it is very dense. It is a little bit unusual to have all your competitors right literally on top of you, as is the case here, but this is how this works when you work in this kind of science. Here's a little closer look at an older version of our experiment that we'll revisit again. If you see at the middle, at the bottom, you see the sort of cylindrical shape that is green at the end. So you will see that on the tour as well. It is now a museum piece. But what you sort of see here is antiprotons. They come out from this antiproton decelerator on the bottom right, and they met with positrons that we get from a radioactive source I mentioned earlier that come up on the left, and it all meets in the middle to make antihydrogen. So in the cartoon version, it looks like this. The antiprotons are captured, or some of them are captured. As I said, they're quite energetic, so we can only capture a fraction. And positrons are in the meantime accumulated from this radioactive source, and then they're brought in to the middle of the apparatus. So that's all this happens in the middle of this giant cylinder you saw. Now, this doesn't really explain what's going on. It's just a cartoon with some spheres moving around. So what actually is going on here? Well, to understand that, we just need to revisit some little physics here. So these cylinders that you saw in the cartoon, and that's also drawn here as two yellow ones, they look in reality like what you see on the picture on the top left. To give you a dimension, it's about 4 centimeters across. Okay, so it easily fits in a hand, one of these cylinders. Now, how do we hold on to these charged particles? Well, if I have a charged particle there in the middle and I apply a big fat magnetic field along the axis, that's what the big cylinder is actually for, what will the particle do? Well, it'll go in little loops around this. Think of an accelerator. That's what these circular accelerators they actually have magnetic fields that point into the ground, and then you make a big loop. Okay. Now, these particles now have very low energy. Okay, so the loops will be very small, so you can keep them inside your apparatus. And in fact, they're so small that effectively the particles behave like beads on a string, and they will just stick to the field lines. Okay, now that's great. So the magnetic field prevents the particles from going out to the sides. So how do we prevent them from going along the axis? Or how do we manipulate them? Because we also need to get them in and out. Well, we do that with these cylinders. On these cylinders, we can put an electric voltage. That creates an electric field that's along the axis. Let's say you have 0 in the middle here, and then you have positive on 0 on the cylinder that's in the middle, that's invisible, and then positive on the other two. Then the two external cylinders will repel this positive particles I have here in the middle, and it'll want to hang out in the middle and bounce back and forth between these two. It'll be in a well. So that's what's on this cartoon, even though it's not really indicated very clearly. I'll have another movie later that shows this slightly better. Okay. Okay, so now we bring the antiprotons together with the positrons, and we hope, effectively, that an antiproton will capture a positron. And then you have a bound state of an antiproton and a positron, which would be antihydrogen. Now, there's something to point out here. Antihydrogen is neutral, as I already mentioned. Okay, so what happens when it's neutral? Well, It doesn't actually care about our electric forces. It might care about our magnetic fields, but our magnetic fields is constant in space, so it doesn't do anything at this point. So the neutral atoms will just fly out and smack into the wall if we don't do anything. And when they smack into the wall, they annihilate, and that's what this is showing. And that we can monitor, and that's what was just shown here. There's a detector around the system that can see what happens if it annihilates. Okay, to return to the original picture I showed you with the two arrows for positrons and electrons annihilating, that's the lines that go between the two blue sugar cubes. Okay, that's actually because these two photons can be detected by these are scintillating crystals in this cartoon, and they can detect these two photons. Now, charged particles, when a proton and an antiproton annihilate, it's a bit more complicated because, of course, they're made of quarks and antiquarks, or quarks, as you want. So in fact, they make these short-lived states called mesons, called pions, and they can be charged, and those can be detected. It's something that looks like a CCD that's in all of your cameras, and that's what these little plates show. And there will be more tracks, so you can reconstruct all these tracks by knowing what passed through and figure out that you actually had an antihydrogen atom. Of course, that doesn't help you study it if it just smacks into the wall. So to figure out how we hold on to them, we have to just take a little step back and look at atoms, because atoms are actually tiny magnets. Okay, this actually also is thanks to Paul Dirac. That was one of the things that came out of the woodwork when he imposed the speed of light from the Schrödinger equation, or special relativity to be precise. Okay, and one of the things that popped out is that these particles, they have spin. Okay, here it's cartooned with a little arrow. What effectively means is that both electrons and protons, so meaning anti-electrons and antiprotons, they have a little magnetic field. Okay, they have what's called a magnetic moment. They look like little bar magnets, very small bar magnets. As it turns out, because the proton is more complicated, it has a much smaller magnetic moment than the electron. Okay, so that's why they're different size here. Now, when something is magnetic, you can trap it, because everything is magnetic, including this frog that you see here. It's not in water. It's actually floating in a 10 Tesla magnetic field. I didn't do this. This was, in fact, Andrew Game, who was in Manchester, who did this. He got the Ig Nobel Prize for this particular experiment. But basically, frogs are diamagnetic. I think the frog survived and was happy afterwards. It's like being in an MRI magnet, except here it was in a magnetic minimum. You can do something that's maybe nicer for animals, and you can have a mechanical magnet set up like this with a spinning top, and then you can hold it with these magnets that's a little bit hard to see in the video. Okay, so with magnets, you can suspend other magnets in space. So with magnets, you can suspend an atom in space. Okay, even though atoms don't really worry too much about gravity, that's one of the things you can find. So we built a new apparatus and updated the graphics a bit, so it looks a bit better now. You can see these plates around. That's what we call the Annihilation Detector. That's the one, these plates that work like CCD chips in your camera that can see charged particles. We have the vacuum chamber, which is the tube in the middle. And on top of that tube, we've now wound this complicated magnet that actually has 3 magnets in it. It has these 2 N coils that we call mirror coils. And then there's this snake-like structure around that makes it an octopole, which means it has 4 north poles and 4 south poles sort of symmetrically around the middle. All of these magnets together make like a magnetic bathtub for the atoms. And that can hold on the atoms in the same way as the magnetic bathtub held on the frog. Okay, we still need these electrodes, so the yellow cylinders we talked about before, because we need to make the antihydrogen in the trap. We can't sort of pour it in if we made it somewhere else. So all of this has to be compatible and in the same location. Okay, so now we see the actual electric potential that we actually have. We have the positrons in the middle. We have so many, they move the potential a little bit. We bring the antiprotons in by just moving the potential a little bit. So here there's a bit more detail on how that actually happens. Okay, we just move the potentials. Okay, so now no one was talking, especially because I can't see you talking on the way I'm running this now, at the fact that an antiproton just captured an electron. Well, that shouldn't be a problem, right? They have opposite charge. Well, just because things attract doesn't mean they stay together. So here's a little bit of a silly joke. You can see lots of things in the world attract, but there's still very high divorce rates around the world. Okay, that's just a little silly joke. What's the point here? The point here is like when you go to bed, you need to lose some energy. If you're too excited, you can't fall asleep. If you are a comet into the solar system and you don't hit anything like Jupiter or the moon, you're going to leave again, despite all the attraction that's going on. Okay, so how does this actually work? how does an antiproton actually capture a positron? Well, it does so in a little game of billiards, because we have a lot of positrons, because those are much easier to get than antiprotons. So by having a lot of positrons, two of them can hit an antiproton at the same time. And as a game of billiards, one of them loses enough energy to stay. And then you've made your antihydrogen atom. Okay. Now, this antihydrogen atom is now neutral electrically. So the only thing that we care about is its magnetism, and it can now be trapped in this bathtub magnetic field that we made. Okay. But how do we detect we have one? We might only have one in there. In fact, in the beginning, we had less than one, if you want. And the volume of this is like a beer can. It's half a liter. Well, we detect that we have it by throwing it away. Because despite it just being a single antiatom, right? Imagine you had a single hydrogen atom in a trap. That would be hard to detect. But a single antihydrogen atom has the advantage that when you throw it away, and you saw that in the cartoon here, when you throw it away, it annihilates. And all this energy from the antimatter is released. Now, it's not a lot of energy seen from a macroscopic perspective, right? It's not going to blow up anything, but it's a lot of energy on a microscopic level, so it's very easy to detect. So we can have that with the detector that was shown there. We can detect them. Okay, that's all great. So we can trap the antiatoms now. Originally, we had very few. In fact, we only had one in the very first experiments we did. We had one for every 10 experiments that we did. So you had to run an experiment, takes about 15 minutes to give you an idea. So for every 150 minutes, we might have had one. Okay, we've gotten a bit better now. So now we have 10 every 4 minutes, more or less 20 every 4 minutes. But the key point is we want to look at it, right? It's not enough to trap it. Now we've held on it, and now we have a chance to actually look at it carefully. So we've looked at it in many different ways already. So I will focus on one way that required us to rebuild all the apparatus. And this is what you're going to see in my little tour today in a little bit more detail. Okay, we rebuilt the apparatus because we want, of course, to do spectroscopy. We did some other experiments first, but I'll focus on the spectroscopy today. A spectroscopy means we have to shoot a laser on it. Okay, we have to excite the ground state, which is called 1s, to this first excited state, which is called 2s. Okay, to do that, you need a lot of laser light because you have very few atoms, and the laser beam is going to be very small. It's about 0.2 millimeters, and it has to hit the atoms. So you have these mirrors at the end here that enhances the amount of light you have available so that you have really a lot of light, because you also need 2 photons, as you saw there in the cartoon, to actually excite the atom to this orbit. Now, an excited atom looks like an atom. We can't see it. So in fact, to see it, we have to destroy it. And as you saw here in the video, there was a 3rd photon that came in and smacked the atom to pieces. So there was just an antiproton left. Well, and that antiproton is not trapped anymore because we switched off the trap. Alternatively, we can wait until the end and look at now how much antihydrogen we had left to see if some of it got thrown away with our laser. Okay. So by tuning the laser frequency, we can find out how the atom responds as a function of frequency. Okay, in the very first, very simple experiment we did, which I will explain carefully now, we ran this sort of experiment 11 times for each of these 3 categories. Okay, we need to know that it's the laser and it's the frequency of the laser that actually interacts. It's because the laser has a given frequency that it interacts with the atom. Okay, so how do you do that? Well, you have a category here called off resonance, one called on resonance, and one called no laser. So no laser is running the experiment in every way exactly as if you had a laser there, just to see what the sort of natural behavior of this experiment is. And as you can see, what we look for is how many atoms do we have at the end of the experiment. After we run the whole thing, it takes actually about half an hour. We see how many atoms are there. And of the 11 trials, we had 142 atoms. So it's about 14 or 13 per trial, as you can see. 142 detected events. Now, if the laser was off resonance, okay, in this case, because we were a bit conservative, we moved the laser away from the frequency we thought the atoms ought to have, that transition ought to have, on the 10th decimal place. Okay, so you have calculated what frequency the atom should have in our magnetic field, and on the 10th decimal place, you move it essentially 1 digit. And that's what we call off resonance. And as you can see, the laser did nothing. 159 with the uncertainty is the same as 142. However, when we moved it on that 10th digit to be on resonance, we kicked out half of them, more than half. As you can see down there, 58% was kicked out. Okay, so we actually managed to hit exactly the resonant frequency in this atom and exactly where it was supposed to be. Now, we refined this experiment. This took a long time. We refined this experiment the next year. So we're talking about now 2018 here. Okay, and did the same sort of thing, but moved around in frequency now. Okay, and that's what you can see here. You can see this, the black curve is the calculation of how this atom is supposed to respond. It's like a resonance on a piano, right? If you hit it right on, it'll respond the maximum. If you hit close to it, it'll respond slightly less. If you're far away, it won't respond at all if you bang on it with a given frequency. Okay, and we managed to measure this transition with all these digits, as you can see down here, compared to the expected one, which has a similar amount of digits. Okay, and what's in the parentheses is the uncertainty we have on this measurement. Okay, what does this correspond to? This corresponds to a precision of 2 × 10⁻12, which means that we compared it and measured it with 12 decimal places, and in agreement with what it should be in hydrogen. Now, as an experimentalist, that's obviously somewhat of a disappointment. A lot of other people are not disappointed, so you can see here an example of some of the responses we get to results from antimatter. There are also some where we open the gates to hell and things like this. But of course, for us, where does this leave us? Well, it leaves us that we have created and trapped antihydrogen, an atom that nature probably has never made. It's hard to know for sure, of course. You can do the calculation, and we've now had the first glimpse inside, right? The first quantum jumps, and we've looked and seen a transition and measured it with 12 decimal places. Now, it's not to the 15 that hydrogen has been measured, but it's a very good start. Okay, and we have seen so far no difference. So what does that mean? That means, of course, that the missing antimatter in the universe is still gone. And since we've seen no difference so far between this anti-world and the normal one, we still don't have an explanation for why. Okay, so we keep looking. Now, what does that mean? It means there are so far no evil twins. Okay, now to put this in perspective, so now I'm going to deviate slightly, but talk about a cousin experiment if you want, just to give some idea, because you have to imagine this as an exploration into the unknown, into the truly unknown. We don't have a model, so we don't have a map, right? In some sense, when they looked for the Higgs boson, they had a map, right? Peter Higgs has predicted that the Higgs boson should exist sometime in the 60s. It took a very long time, and lots of intermediate confirmations that it seemed likely that it should exist to get there, but at some level there was a map of where to go and look. Now, we don't have a map because there is actually no model for how the universe ended up being asymmetric in the way it is. So we're just looking, but we're trying to look the best way we can, which is trying to go the most precise tools that physics can give us. Now, there's a recent example where using precise tools have given an interesting conundrum. Okay, so we go a little bit away from antimatter for a second here and think about how do you measure the size of the proton, what's called the proton radius or the proton charge radius. Well, what would you do if you had a proton and you want to know how big it is? Well, one way you can do this is to shoot electrons on it, a lot of electrons on it, and see how they scatter, and then you can reconstruct from this pattern how large the proton is, and that gives you some precision. Now, and that has been done, of course, for many years. Electron scattering is an old technique. If actually already Rutherford was shooting alpha particles at nuclei and could say something about the size. But you can also use spectroscopy. Why? Well, think about what an atom is. Well, here's an atom. You have an electron. It goes around the proton in some orbit. Spectroscopy is measuring the energy difference between orbits, basically, right? But of course, this cartoonish version of an atom is not actually how atoms look, right? They're not little planets. Electrons are not little planets going in orbit. We're now in the quantum world where it's all probability distribution. So in fact, the electron is sort of smeared out around the proton, and crucially, inside the proton. So electrons can be all over the place inside an atom, including inside the proton. Now, when an electron is inside the proton, it sees less of the proton. So the energy changes, right? The energy it has in an orbit where it spends time inside the proton is going to be different from if you hadn't done that. That means that by carefully measuring these transitions, you can measure the size of the proton. And they all agreed until 2000, now I have to be correct, about 2010. Well, we'll get the numbers in a second. This all agreed, and everyone is happy, right? They did measurements in spectroscopy, they calculated the size of the proton, it agreed with the scattering experiment, and the case was closed. Now, some clever guys came along in about 10 years ago, I think it is, we'll have the numbers in a second. And then they said, but what if we replace the electron with a muon? Muon, in many ways, is like an electron. It's a heavy cousin. It doesn't live as long, so this is not an easy experiment. It lives about 2 microseconds, or 2.6. But it has 200 times the mass of the electron. Now, if you do the very simple calculation on hydrogen, what's it going to do if it has 200 times the mass? Well, if it has 200 times the mass, it'll be a lot closer. And the wave function will look much more like this. It'll spend a lot more time inside the proton. Okay, so the energy levels of the muon are going to be much more sensitive to the charge radius of the proton. So by carefully measuring that, you can get a measurement of the size of the proton, right? And when they did that, they got this. 2010 was the number here. You can see they got the red line out on the left. They repeated it again slightly better in 2013. What you see on the right side here was all these people who agreed historically. They were all sitting, as you can see, 8 standard deviations away, the new measurements. Interestingly, everyone agreed that the new measurements were so clever that they were probably correct. And since then, I have to say, they have improved on the hydrogen spectroscopy, but in particular, what they've improved is it turns out the way they extract the proton charge radius from their measurement, because of course they're not measuring it directly, seems to have been flawed. And there are also people who have redone electron scattering measurements to be more careful. So now it turns out that they all agree, but they only, of course, started looking carefully because the muon guys came along. Okay, so when you look very carefully, you may find interesting stuff. And that's sort of the philosophy we're applying here. So I will thank everyone for listening and see if I can somehow see the questions here. I don't have my mouse, because it's a bit inconvenient. If there are any questions at this point, we will. I have to do something here. What do I have to do?
Hi, Niels. So there should be a Q&A thing in the bottom right.
Yeah, there is, but the bloody thing is taking my mouse. There we are. Okay, it'll look slightly different for you then. It also put something else that has been.
You can probably stop sharing screen, or you're going to do the tour, aren't you?
Yeah. Yeah, I'm going to do the tour, so I will just use that in a little bit. Okay, so there are a lot of questions here. I think, okay, there's not too many yet, so we'll see if we can go through them. How has quarantine affected your work? Well, CERN is closed, and the university is closed, so we mostly work from home. Now, CERN was already sort of in shutdown mode because it's actually rebuilding a lot of things. So, and it has been shut down in 2019 and 2020, which means that right now would have been a really good time to visit CERN normally, because you can see many more things when it's shut down. But of course now it's like really shut down, and they have a maximum of 300 people coming in on a daily basis to sort of run basic services and things, make sure things don't fall apart and buildings burn. But we've been writing articles. We had a very good experimental run last year on something that wasn't antihydrogen but related. So we've been working on articles for that. So I think what it mostly has affected is that my teaching has been done online. My teaching in Swansea, we've done that over Zoom. That has gone fairly well, at least when you ask the students, they seem to be reasonably happy. I don't know if, so that is at least possible. I have traveled a lot less, which is not so bad, but the difficult thing is, of course, the schools are closed, so you've had to somehow manage to work from home with the kids running around, so you end up pacifying them with some TV more than you would normally do, I think. So someone is asking here whether matter-antimatter annihilation is similar to destructive interference in waves. No, I wouldn't say that has anything to do with each other as such. It is not dependent on the wave nature in any way. And then does string theory predate the Big Bang? Now, no, that's easy to answer. Prem was here yesterday. He could probably say more about string theory. String theory is a way to solve some of the pile of problems that CERN is trying to solve theoretically. There's currently no indication that string theory is any better than anything else that describes what already exists. But in principle, nothing predates the Big Bang. At least we have no way of knowing if anything predates the Big Bang. To the extent that our model for the Big Bang is correct, there is no memory of what, if anything, was before. And now they say, when you say the closest thing to an anti-universe, does that also mean that antimatter is affected differently by the 4 fundamental forces? That is exactly the question we're trying to answer. Okay, now, of course, when you measure on an antiatom, the primary force that runs in an atom is oh wait, so how do I say that this has been answered? Because I don't think you can see the questions. Okay, I'm just answering this live. Wait, I'm going to do this. There seems to be buttons I can click here. Wait a second. Okay. So we've done, now I got lost here. Okay, today, when you say that, it's, yeah. Okay, so what we're actually trying to find out is in which way, if any, antimatter is affected differently by the 4 fundamental forces, right? By very carefully measuring, doing spectroscopy on these atoms, or by other techniques that other people, for instance, doing gravitational measurements of antihydrogen, we are trying to find out if there is any clues, if there's any way in which these 4 fundamental forces might act differently, or if, for instance, there could be a 5th force that interacts with antimatter differently than matter, and in some way it's been camouflaged and we've not been able to see it before we compare matter to antimatter. That's what this is all about. So we don't know yet. According to the standard model, there is no difference. According to the general theory of relativity, antimatter is nothing special. So according to our models, there's no difference, but of course our models are the ones that also fail to explain why we actually exist. So they certainly have at least one flaw. Okay. So the next question is, today we accelerate physical matter and collide them to create antimatter. How did pure energy convert itself into particles if there was nothing to prompt it to do so? There was something to prompt it to do so. There was a lot of energy around. It's all a question of probabilities. The probability in the amount of energy densities we can create. We can increase the probability by smacking things into other things, because kinetic energy in itself doesn't actually do anything. It's just something moving through space. So in some ways you can say what happens when these particles collide is that the particles, let's say the protons on the protons in the LHC, the particle bend, okay, and the charged particle that is accelerated emits radiation, and you can get enormous accelerations in these collisions. That's essentially what the collisions are. It's the same way as you make X-rays at your dentist. If you ever made X-rays at your dentist, you shoot electrons at a copper target. That's how they do it. And these electrons, when they break, they emit what's called Bremsstrahlung, braking radiation, if you want. And that radiation, if it's strong enough, it will be similar to the situation in the Big Bang, and then you can spontaneously have pair production. Okay, so you don't as such need anything to prompt it. It's just that we don't know how to create this radiation any other way. And then, okay, this was an early question that I think I did explain. If you need to accelerate these particles to high speeds to make antimatter, won't you have to slow them down again in order to store them and do research on them? That's exactly what I've been talking about. That's why we are at CERN, to have the energy. And we're also at CERN to have the antiproton decelerator that gets them down to low energy. Okay. Does the antiproton always split in the same direction? I presume this referred to the drawing. The antiprotons are negative compared to protons. So with the right magnetic fields, you can just direct them, and that's what we do. Okay. And then there's a question, what's the difference between the alpha experiments and other antimatter experiments? That's a longer story. I guess I can talk about that when we do the tour, but well, okay, so Aegis experiment, I can give a short version. The Aegis experiment and the G-bar experiment that you may have noticed on the map, they both focus on antimatter gravity. and they are relatively new. Well, not so much the Aegis, and they go different routes. There are different methods. They do not go via a trap, at least not at this point. They try to make antihydrogen in other ways, whereas we have developed a lot of expertise in trapping, and we believe that to be the right route. So generally, the philosophy here is that people do slightly different routes, and of course, we think we have the best idea, and we believe that some people might change their opinion to follow our, at least some of our ideas in the future. But that's always open. And CERN actually, while CERN is not specifically involved, it's a little bit involved in the Aegis and some of the other experiments. They're run by scientists from all over the world. In our experiment, we are from about, what is it, 5, 6 different countries, institutions from 6 different countries, about 11, 12 institutions, and about 50 people in total. And CERN encourages people to take different routes because, of course, a priori, you don't necessarily know who has the best idea. So competition is good for that, even friendly competition. Okay. And then there's a question of whether we can do what was done to the flying frog to humans. And I think the answer is yes, in principle, but you need really, really strong magnetic fields that no one's able to make. I think that was a 10 Tesla field. And basically, since you have to compensate gravity, well, you need probably to multiply that up more or less with the scale of the mass. And 10 Tesla fields are about the strongest we can make. And you can see we can also only make them in very small volumes. So this doesn't seem like anything that's going to come up now. Then there's another question. What's the longest antimatter has ever been stored in one of these traps? Well, it has been stored in our trap. We store antihydrogen for up to about a day. However, that is by no means the record. There's an experiment called BASE that just looks at antiprotons and in particular looks at their magnetism. And they have stored antiprotons for more than a year. And I believe they may still have some from 2 years ago. So in principle, this is only limited by the quality of your vacuum, because technically, if the standard model is correct, at least on this aspect, antiprotons should live as long as protons. And as far as we know, they have essentially infinite lifetime. Then there's someone who says that some general universal theories, unifying theories, propose ways in which antimatter could have disappeared in the Big Bang. Right now, I'm not an expert on any of these theories, but there are a lot of ideas out there, but I wouldn't say that any of them are models in the sense that they have made any testable predictions that people can go and look for. As far as I'm aware, I have certainly never seen it, because then people would go and hunt for them. Like there is something called CP violation that's looked for in great detail. And that is a tiny difference between matter and antimatter that has been detected and is measured. But it is so tiny that so far nobody's come up with any way in which it could actually do this on a universal scale. Next question is, as electrons can be found inside the nucleus, does this mean that the plum pudding theory is more accurate than once thought? Well, no, not really, because the plum pudding theory wasn't really a very elaborate theory. It didn't predict anything whatsoever. So I wouldn't really say that. At least it's not in that sense there inside. And then what triggered the Big Bang, and do you think the world will carry on just expanding? Well, I don't think anyone can answer what triggered the Big Bang, since time also began, so it's kind of hard to know. And is it even, I think in the current model, I'm not even sure it's a meaningful question. That doesn't make it a bad question. It just means it may not be meaningful. It may not be a question that you can even ask in the Big Bang model. Prem or Simon might be better positioned if they're around. And then there's a question if the world will just keep expanding. I believe it probably will. Currently, the evidence is that it's accelerating outwards, right? So I don't see any reason it should stop. I have never been to the Vatican. Is it worth a trip to Rome? Absolutely, yes. And also Pompeii, which is just next door if you're in the neighborhood. But I think right now is not a good time. Then there's, can students do a year in industry at CERN? Yes, in principle. There is nothing to hinder that. CERN has programs for that you have to be admitted into the CERN program. So this is clearly something that requires some preparation, but it's possible. And CERN pays. It's a CERN technical studentship, it would be called in this case. Do you like the theory stringy or loopy? Okay, I think that's a joke. Is strange matter dangerous? I think that matter, so to say, has been closed. I don't think it is. And I think that has been demonstrated a lot of times. It doesn't live very long. And there was some weird calculations that showed it could be dangerous, but I think those have been laid to rest. Would using third generation, okay, now it's getting really far away. Would using third generation tau particle aid in getting a more accurate proton charge radius? Ah, you mean rather than a muon? Yes, in principle, but I don't think tauons, they live long enough that that's possible. Tau particles live long enough, so yes, in principle, I think that's true. Do you think axions will be discovered? I have no idea. I don't actually have an opinion. I have seen that birds can use quantum mechanics for navigation. Okay, maybe I should stop. There's really a lot of questions here. Open 34. I think maybe I should go on with the tour and we take these questions that come along. What do you think, James? We have some time limit here, I guess.
So I think probably we can go on for the tour now. There's still some good questions, but
yeah,
the flow, I think it might be good to go on to the tour now.
Yeah, just so that we at least move a little bit ahead with that. So I think I will, so this is going to be complicated now. Let's see if I can do this. No, that didn't work. No, that didn't work either. Okay, I'm going to have to go here. Okay, so I wanted to go to this because this is just to give you an overview. So you've seen some pictures now. So this is sort of a mechanical overview of the hall we're going to go into. Okay, if people are really keen, I have possibilities to go other places in slightly lower resolution. We're going to start up here. Okay, so you saw this picture before. The alpha experiment sits down here. The other experiments, there's the one called Aegis that someone asked about that sits here. The Asakusa experiment sits here. This doesn't show all the equipment that's in the hall, by the way, this picture. The G-bar experiment sits over here. And this Elena, I haven't talked about at all, effectively. It was on the drawing, though. It is a new little facility. It's an add-on facility that CERN has built that will be fully operational when CERN comes back online next year. And it'll give us antiprotons at even lower energies and actually, in some ways, more of them. Well, effectively more of them. So it'll be a big boost for this kind of research. And now I think I have to find a way to go to the view, but I believe I have to stop the share and change the share to something else. There you go. Okay. So this is the entrance I just showed you. So it's just scrolling around. It's a big hall. As you can see, now you can be lucky you're not actually in person because it's really noisy normally. There's a lot of pumps around. The hall is about, well, as you saw, the machine is about 180 meters in circumference. Okay, so there's a big yellow blob. You see at the end, it's a rolling bridge crane that you can use to move, that people use to move things around in the hall, including us. And we'll now have to go around the corner here and down the stairs. This is literally a tour. To go into the hall. Okay, we're just going to move down the stairs here. So as you can see, this was actually literally photographed like 2 weeks ago. So this is the state that it is in right now. So if you remember from my picture before, there was this thing with the green end, this big cylinder. That's our old magnet that we used to, that we trapped the first antihydrogen in fact. Okay, and you can see how this big cylinder is hollow inside where the mouse is. And this thing that sticks out is basically the whole system with the trap and the special magnets for trapping antihydrogen that sticks all the way through, and it's only mounted at the other end. So the big cylinder just gives you, this is what's called a solenoid, and it gives you a big fat, big strong axial magnetic field of about 1 Tesla. Okay, but it's not being used anymore. Normally it's a little bit easier to see it in exhibitions. We're going to walk down the corridor here. What you can see at the other end of it, let's see if the next one gives a slightly better look. Okay, this can be a bit confusing if I go too fast, I suspect. So I'm going to zoom in here because you will recognize this possibly later. You can see sticking out here at the end Okay, the cylinder sticking out, that's the other part of this cryostat that's installed, because these magnets that we use to trap the antihydrogen, they are superconducting to get enough magnetic field. So you have to run very high currents, and these gray things up here on the top, those are where we connect room temperature power, which is about 1,000 amps. So that's about the amount of copper. This is copper, even though it's gray, it's coated. You need about 1,000 amps to run these magnets, but of course, 1,000 amps at room temperature has to run in a very thick copper piece, which is what these flags are. And then the whole magic is that, well, the superconductor has to be at about 4 Kelvin, okay, which is liquid helium temperature. So somehow you have to get your current at room temperature that comes out of your power supply and out of your power plant at room temperature into the 4 Kelvin area. And of course, the problem is that copper that transmits, or anything that transmits electricity really well, also transmits heat really well, because it's the electrons that does both. So you need some sort of onion structure where you slowly go down in temperature. You can't just stick a copper bar into your liquid helium bath. It would make an enormous glacier of ice on top. And in fact, that's what this whole tower thing here is about. It's about transitioning from room temperature up here on the top, in principle at least, to liquid helium temperature down here at the bottom on the inside. And of course, it's all like a thermos bottle, so it's shielded in all kinds of ways. Now, this was home built by us, ourselves, and our students. So it was not the most efficient cryostat on the planet. It had a bit of an ice ball on top, but it did the job. Okay, now I'm going to scroll around here. I'm not quite sure how well this scrolls when you're just looking at it from far away, and we keep going along the corridor here. Okay, we're just going to jump to the end here where you see the ventilation tubing. Okay, so that has been taken out because they're rejigging the ventilation, because in fact it had to take, what you can see we're walking on here, we're actually walking on top of this accelerator. You see these, this is concrete blocks. I don't know if they're easier to see in another place. You see them here as well. The gray stuff is all concrete blocks. They're stacked like Lego bricks on top of each other to make like a Lego brick tunnel underneath. So we are on top of the accelerator here that runs in the tunnel underneath. The reason why you have all these blocks is, of course, that when the accelerator runs, there's radiation, and people have to be able to work in here at the same time. Like originally, this hall was actually had 2 accelerators in it and no concrete blocks, because nobody had to be in here because there were no experiments in this hall originally. But then they had to build this tunnel so that people could build the experiments. And now you can see here the access to our experimental area, which will go down through this yellow door that actually, if you actually were visiting, you wouldn't be allowed to go down here. So we'll just go in here. We're now slightly down. We were just up here before, above the yellow door. We're now slightly down on this sort of intermediate level. You could just about see the floor down here. So that's the height, which is about the, so this level is about 3.5 meters above the floor. So there's maybe about 5 meters to the top of the concrete on top of the ring. You can see how it's all stacked up. There's these cross beams. And on this floor, we have most of our electronics. As you can see, this was not installed by engineers, but by physicists, which is why it looks a bit messy. It is also in a state of flux at the moment because we're redoing a lot of things. Okay, we can go along. This room you see here is our control room, which I don't have a picture of right now inside. We can go along here. And now we're looking, we're above the experiment. There's more electronics here. We're down, we're going to go downstairs in a second. We're looking down on the experiment that's below us here. There's electronics even on top of the experiment. We had nowhere else to put it. And underneath here is this tower, the new version of the tower you saw before. Okay, and why we're looking, because all of these black cables, those are the cables that bring the power supplies that sit in this red rack down onto the equivalent feed-throughs, the ones I showed you before, that sit down here, that now bring, in the original version I showed you before, we had just 4 superconducting magnets on the inside. This new experiment that we're running now has 8 for various reasons. And this is the kind of cable you need at room temperature to bring it in, whereas the magnet is actually wound with a cable that's only 1 millimeter thick. Okay. And you can, and then actually what you see here also, when you go back to this place, you see like all this aluminum structure and a big emptiness here. Okay, that's because there's a new vertical experiment that we're building. that has been temporarily, it has been installed once, but it's now been removed for refurbishment. And we are planning to measure gravity in that. And well, if you want to measure gravity, it makes sort of sense. It should be vertical. But the idea is we have a vertical version of our trap. So the same thing as you saw in the videos about how we trap and make antihydrogen is supposed to apply in this. We have not actually made antihydrogen in it yet, but we have trap particles in it and have them together in it. And that's also going to be here. And in fact, that's what all this structure you see up here on the top is to bring all the cables to the top of that apparatus. So it is really, really big when it comes in. The top of it is about 8.5 meters from the floor. And I just go along the corridor here. And here you can see the equivalent electronics to the other racks that is necessary to run all that. Okay, that sits here. And all these big fan things here and things next to the big fans are the power supplies for this new experiment. And all the power runs up here and is then normally connected to the experiment up here. Okay. But let's roll around and go down the stairs again, further down the stairs to the floor. Okay. Yeah, that's a little bit, we can zoom back a little bit. Okay, we have a big yellow door here. There's some power going here. Let's just, to orient ourselves, we'll just look up the stairs. So we just come down these stairs here. Okay, they're distorted a bit when everything is this close, right? We came down the stairs. Then here on the back, you see this danger laser sign. That's our laser room where we have the lasers that we use for the spectroscopy and where we have the system that allows us to reference these lasers to the absolute frequency. We do this via our GPS antenna that's on the outside of the building. And then we have this yellow door here, which is open right now. That would normally be closed if there's beam because there's radiation in the area. Well, a little bit at least, and you're not allowed to go in, but we will now go inside. And the first thing we see when we come in is this device, which is in particular Swansea's contribution, which is the positron accumulator. So in here, in this octagon-shaped box here, where we have a radioactive source, you can see the radioactivity symbol here. That's where we have a sodium radioactive source where positrons come out of, and they are then moderated so they come out at electron volt energies. Follow along these yellow things here are magnets. They follow along here, and they are accumulated in this big magnet here. Everything here is cylinders, right? It's all the same principle with cylindrical magnets. And then they accumulated in this device, which is called the positron accumulator. And then when they're ready, they're shot across to the experiment. Now, originally, this whole device was standing right next to the experiment that I showed you. But now, because we have to have space for all this stuff, there is a whole beamline here that can transport the particles along. So we will go along this beamline here. James, if there are questions to the pictures, maybe you can read them up. If there are specific questions to things during the tour. Okay, so we're just walking along the beamline here. You see here more magnets. Basically, there's a magnetic field along the axis all the way here. Now, there's one thing that's worth looking at here. If we zoom in a little bit, I think we should be able to see it. We can only see it. You can barely see it. You can see the haziness here on the picture. It is not a lack. Well, it's hard to see. It's not a lack of resolution, this haziness. Okay, this is what's called a bellows. It's literally like a bellows. You see another one down here, but this bellows is interesting because this whole device here is a translator, so it can move up and down, and it moves instruments inside the vacuum chamber. So in order to have mechanical movement inside the vacuum chamber, but having stuff that sticks in, you see cables on top going into this. This is so that we can move devices around inside that we can put in the beamline, so in the path of the particles, the positrons in this case, coming from the accumulator, to measure how many there are, if they're going in the right direction, and so on. So we have a lot of those kind of devices, and the bellows allow you to take movement from air into the vacuum chamber, okay? And a lot of these other things we see here are valves and detectors. So this is a pump. Here's a detector for measuring the vacuum. Here's a valve. Down here, there's another pump, this red one. There's another pump. And what you see on the wall here on the right is pressurized air distribution, also clearly homemade, as you might be able to tell. And this air powers all these valves so that they can go up and down. Now we're underneath this mega structure that originally holds a huge vertical solenoidal magnet. Okay, and you can see we have this really complicated piece here. with lots of magnets. All this black stuff is magnets that were manufactured at RAL in, now I have to remember, it's close to Swindon. Right now, I've just forgotten the name of the town. It's the Rutherford Appleton Laboratories. They manufactured this for us. And this is we call the interconnect, because it allows particles coming from here to be shot vertically into the apparatus, and particles coming from here also to be shot vertical, and sometimes to be shot horizontally to the other apparatus. So it's basically sort of a change track. And in order to diagnose what on earth is going on inside that, there is normally another translator here that you can't see, and there's another one here, right? So these instruments we use to see what's going on inside. And all this big aluminum structure is to be able to hold the new thing. Then you see another piece here, that's water distribution. You need cooling water for all these magnets, because all these magnets here are normal conducting. So it's basically, these are magnets, the black ones here. So it's basically just copper wires. They get quite hot. Now we're really underneath a pile of electronics here, as you can see, and pile of cables. We see more beamline here, and eventually the beamline comes down here and disappears into this. And there's a black box here. Now everything's black, I admit, but that's where the laser can come in or out, okay, of the main apparatus. From this side, we don't see the main apparatus very well, because basically there's no light. Here you see just about the indications of another translator. You can see the spindle here that allows us to move things inside, okay? And then we go through this dark tunnel here. This is where all the laser stuff comes in. There's another black box here. You can just see the light between, not so much to see here. And then we come down to the beginning of the experiment. So this is where we trap the antiprotons in this green thing. We'll see it a bit better from the other side. It's called the catching trap. We trap antiprotons that CERN they give us, right? And then we shoot them on. So we'll just go around here to the end. So this is where the beamline from CERN comes out. So as you can see, it's taken apart because they've been refurbishing it to allowing this new ELENA machine to shoot antiproton to us at a lower energy. So there are no magnets, as you may notice. There used to be a lot of magnets here, but it's now all so low energy you can do it with electric fields, which has some advantage, quite a few advantages for us. And eventually this will all be connected here. And here, this is one of the big fat valves, right, that can open and close. So that's basically closed now. There's still vacuum inside. Here you see this green cylinder, which we'll see slightly better from the other side. Okay, that's a magnet. Okay, that's a smaller magnet than the other ones. You can just see a cylinder sticking out here. That's the cylinder in which we have the particles. That's the vacuum chamber where the electrodes are inside, so the yellow cylinders. And this provides just an actual magnetic field. This also gives you a bit of a view. So underneath here, there's a big cylinder that you can't really tell from this that also makes a magnetic field. But all these other things that are standing around here are thermal bottles, effectively, for either liquid helium or liquid nitrogen that we use to keep the experiment cold. So this particular one here in the middle of the picture is a big one that can contain 1,000 liters of liquid helium that we use as a buffer, because we need continuous flow of liquid helium into the experiment for it to actually stay cold.
Niels, there was a question.
Yeah.
And it's, is it common for somebody to accidentally pull out a cable when walking through that arch, causing a problem?
If it was common, we wouldn't get anything done. So fortunately, it is not common, but it has certainly happened. But fortunately, most people only pull out one cable at a time, and it's relatively manageable to diagnose that. Unless it's actual sabotage, which it would be harder to, well, it's also hard to protect against, but that has at least never happened, at least not to us. There have been some histories in the world of physics of sabotage of other people's experiments, but not here. So here you see it from the other side, you see the cylinder and all the pipes, but yes, it can be a nightmare to reconnect something. Here's another translator, okay? And here you can just barely see that there's a big fat cylinder here behind this black box. The black box is there because else people couldn't work here when the laser was on, right? So to avoid people being hit by the laser in the eye or any other thing. What you also see here is this blue thing. That's a camera that actually looks, because inside here we have what's effectively a fluorescent screen. So one way you can detect how your particle beam looks is to put a fluorescent screen in the way and image the picture on a camera that you can then read out and use to monitor your particles. Right, and we can keep going along here. Now it gets really tight. This big thing here is a power supply. We're now underneath the electronics platform that we were on top of before, right? And you see the big doer is right next to us here, this big 1,000-liter one. And you see all this mumbo jumbo on the top here is basically gas management of the helium gas, because we have to maintain a constant, very specific flow across. So there's a lot of remote control, electronically controlled valves here. And this is all things we built ourselves. So that's kind of different from the big LHC experiment that you may have heard of in another context, that a lot of this is essentially home built, or at least built by students and postdocs and myself. And we go further here. Now you see this structure here sits on the floor, and that huge is the one that is normally supposed to sit on the bottom frame that we passed by before. Okay, so this whole thing, this enormous thing, go on top of that, and it has the whole structure inside it. So there's a big cylindrical magnet that goes inside here that goes all the way to the top level, which is this platform. This is about 4 meters tall, this device, and it sits on top of this 2-meter tall platform. We can take a sneak peek here in next to the beamline. Now we're really underneath here. Okay, so here you see this bottom frame, this frame that holds everything on top of it. Okay, I probably shouldn't move too fast. I don't know how efficient the web has at this. And here you see again another translator that we saw from the other side, and another camera, right, to look at it. And down here you see a pump. Okay, so it's really important. And that was what one of the questions was about, how long you can keep it around. It is all about the vacuum. So one nice feature about cooling everything down, and an important feature actually, about cooling everything down, is that once it's all cold, it works like flypaper, all the surfaces. Okay, so think about a cold railing in the winter. Don't put your tongue on it. Here's a drawing of what the whole thing looks like with all of it inside and all the stuff that comes on top. So here's this tower with a transition from room temperature to cold of the power that's going to come in. This is all going to go on top, right? You can see we are down at floor level here. So basically this drawing is hanging at about this level on the drawing. And the big frame you just saw is all of this. And it goes all the way to the top. So this is for people to figure out what they're supposed to do if they're lost in the actual experiment. So you see, this is the structure. These big panels here are scintillating panels. What happens is that when pions, so in particular pions, go through these panels, they make this plastic material they made of light up. And this light is collected at the ends here and detected by photodetectors, in this case, essentially silicon diodes. And that we can then see that pions went through, and that's how you detect annihilation. Now we come out slightly more open space. We're back to the accumulator here, okay, that we saw from the other side in the beginning. Okay, you see now here the bottom frame a little bit better. This top frame, this foot is then going to go over there in principle with the whole magnet on it. The magnet that's standing here in the middle is a test stand we use for testing. And now you see yet another frame. We're a little bit in frame land here. Okay, this enormous frame here serves only to construct the apparatus, because there's the big magnet that has to go into the other thing. But inside that big magnet, we need all the other magnets to trap the atoms and all the cylinders to trap the charged particles. And they all go into this very, very long tube that is then stuck down this other cylinder. And it's basically a long version of what you saw sticking out in the very, very beginning. Okay. So this is what
there are some questions. If
yeah.
So there's a couple about the working environment. So do all of the machines run constantly? Are they ever turned off for anything other than maintenance? And related, is the temperature in there very warm, or because of all the equipment? Or an interesting thermodynamics one, is it very cold because of all the cooling?
Well, it is the whole hall is air conditioned, because the equipment can't take two fluctuating temperatures, and in fact we have a lot of equipment that doesn't want fluctuating temperatures. So the hall is air conditioned with very powerful air condition, so it's kept within about 2 to 3 degrees, so that's stabilized. The liquid helium, of course, if we just release that into the hall, it would be kind of cold. Yes, but the liquid helium boils into a recuperation system, because helium, just the gas, is actually very expensive and very rare. And if you release it into the air, it actually escapes from the planet, so it's just lost forever. So don't do that. So that's recuperated and re-liquefied in another place at CERN. But the first question was about, sorry, I already forgot the first question now.
Do all machines run constantly?
Yes, so the machines, so as you can see now, everything is off. There's 2 years of rebuilding and maintenance shutdown. Normally, all machines run at somewhere between 7 and 8 months out of a year. And there's a 4-month winter shutdown that starts just before Christmas, or it depends a little bit on the machine. It could start in late November. And that's for regular maintenance, because there's a lot to generally regularly keep up to date and maintain and renew and so on. So there's every year there's a shutdown of about 4 to 5 months. And then when they run 24 hours a day. So when we run, we man the experiment 24 hours a day, even if we don't necessarily get antiprotons 24 hours a day. Now, here we see the positron accumulator from the other side. I just wanted to, because actually the photographer went inside, so you can see this tube here, if I can find it, right? It's just a very, very long stainless steel cylinder. That the difficulty thing is it had to be really, really straight, because you can imagine the particles inside, they follow magnetic field lines that are really, really straight. So if this is not really, really straight, first of all, it wouldn't fit. And also the particles wouldn't actually just follow the cylinder, right? They would follow the magnetic field lines. So this whole thing, including this structure that you can see, it looks like it's a roof. It is not actually a roof. It is the cryostat structure itself, this bit, that will sit on top of the other frame that now we probably can, it's in the end, it will sit on top of this frame when the magnet is in this frame. But we have to be able to work on it at the same time. Here's a little test stand that, if we look at it again here, right, it's the little cryogenic test stand, in fact, where there's a cryogenic cold head, because you can be cold in 2 ways, essentially. You can have your own refrigerator, or you can use someone else's by having cold liquid being transported. So for the big parts of the experiment, that certainly doesn't need the oscillations of having your own fridge, because of course a fridge oscillates, it vibrates. There we use the liquid helium. For other things, we use basically a cryo cooler, which is just a very good fridge, and it cools down a stick if you want. So there's a stick in the vacuum chamber here that allows us to cool down smaller subjects and test them.
So Niels, a related question to the cold finger. What's the level of the vacuum obtained, and how long does it take to reach this level of vacuum?
So, well, the level of the vacuum on the very inside of the antiproton sections, where we have antiprotons, it's about 10 to the minus 14 millibars. So that's about 10 to the minus 17 atmospheres. So it's quite low. Our neighbors who can keep antiprotons around for more than a year, they have about 2 orders of magnitude more, so about 100 times better, I think, or maybe it's even 1,000 times, I'm not sure. Our lifetime of antiprotons, we have measured to be something like a day, maybe half a day. Antihydrogen lives about 10 times longer in principle. So we have not actually measured the lifetime, we've just kept it around for a day. A related thing to talk about is, now we're here, the way we get to this vacuum, that probably will better explain how long time it takes. The way you get such a good vacuum is that, of course, in the beginning, you basically start with a vacuum cleaner, and that's what you see down here. That's what's called a rotary vane pump. It's basically just a shovel, like you have in a vacuum cleaner, that shovels air out of the system. Okay, at some point, a sort of simple mechanical shovel just doesn't get it much better. So you get to what we call vacuum cleaner vacuum, though these are probably better than vacuum cleaners. And that's about 10 to the minus 6, so a millionth of an atmosphere it gets to. 10 to the minus 3 millibars, to stay in the millibars, which I'm more familiar with for this purpose. And then you switch on what's called a turbo pump, or turbomolecular pump, which we can see an example of here, and this red one, in fact. Well, basically this. A turbomolecular pump is also still just a shovel, but now it's typically floated on magnetic bearings, and it rotates at a very high speed of thousands of revolutions per second. And that means that it can just suck out more. Now, turbo pumps can then get you down to maybe 10 to the minus 7 millibars. Okay, so a millionth of a millibar, or a little bit less. They can go a bit lower, but now you run into some fundamental problem of vacuum. which is that you have to clean your place really well. Okay, that's maybe no surprise that you have to clean it. So it has to be clean, there has to be no fingers on it and things like this. But there's even a bigger problem is that there's own limits to how much you can actually clean. Because what happens is that obviously at some point during manufacture, well, at most of its life during manufacture, whatever it is you want in your vacuum chamber has been at 1 atmosphere. When you suddenly put this in a vacuum chamber, it is no longer 1 atmosphere. It's, well, seen from 1 atmosphere point of view, it's essentially 0. Okay, so the equilibrium that there is at 1 atmosphere between the air and what's in the material is now no longer an equilibrium. Okay, for those of you who've been diving, it's a bit like getting the bends or diving sickness. If you dive down to say 2 atmospheres of pressure, you will have a higher concentration of nitrogen in your blood, which is not a problem as long as you stay there. But if you too quickly go up, this nitrogen is no longer in equilibrium with the surroundings, and it rushes out in some sense, or it comes out as bubbles, and it gives you the bends. It's like when you open a Coke bottle or a soda bottle of any size, kind of like, it's exactly that. And stainless steel, which most of this is made from, is no different. Stainless steel has reached some equilibrium with nitrogen, with water, with oxygen, with whatever it's in the air, and that will now boil out and keep boiling out for essentially ever of your vacuum chamber. So that's why I'm saying the turbo pump can only get you to maybe 10 to the -7 if you by just cleaning. So what you then do is that to accelerate this process, you can't really clean it in the sort of traditional sense, but you can accelerate the process, and by that way cleaning it, and you accelerate it by heating everything up. And that's why you see these enormous amounts of aluminum foil. This is actually aluminum foil here in random places around this experiment and in any physics lab you would ever go to. Okay, because that's used to distribute the heat from these heating tapes. That's the orange things here. These heating tapes are wound around. You wrap everything in aluminum foil, both to save energy, but in particularly to heat it up homogeneously. Because of course the tape will heat most exactly where the tape is. And as you know from the railroad probably, or from bridges, if you heat up things at a different rate, when you heat up and change the temperature of something, it'll change size. Now, if you change the size of, for instance, the connection point that you can see here, there's some screws here, right? This bit is connected to that bit with these screws. If you heat this up faster than this fast, they will change size at different paces, and you might have a leak. So you have to wrap everything up carefully and make sure and do the heating very slowly and controlled. And that can take easily a week to do that bake out. And then after that bake out, still with the turbo pump on, most of it, you can get to maybe 10 to the minus, let's say 10 to the -9. Now is the tricky point where you actually stop the turbo pump. You close it off, and then your whole vacuum system is now metal, 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 metal. There are no holes to the outside world anymore. There are possibly some windows, but that's it. There's no mechanical throughput anymore to the outside world. So how you get further down, there are a number of ways, but let's stick to the way that we can't see it here. But you have something called an ion pump, which works like flypaper. It basically has a big electric field inside that rips apart any molecule that passes inside this field. It rips electrons off, charges up these particles, accelerates them into some structure that tends to keep them better than stainless steel, which is some carbon structure, typically some graphite. And basically it bombards them in, and it sucks in these particles. Well, it sucks. There's no sucking anymore. They're just random movements of molecules around the space. But any molecule that goes into this pump tends to not come out. Okay, so it's like a black hole for molecules. And that will pump and compensate for the eternal outgassing that there will be from the stainless steel, despite all the baking. In addition, when you cool it down, the cold surfaces, as I said, work like flypaper. And they also cool it down further. And that's how we end up to the 10 to the -13. With ion pumps, you can maybe on a good day get to 10 to the -11 or something like that if you're really good and don't have too much mess in there, which we do have, so we don't get quite that low. Okay, so I think that covered that. We'll just go to the end here. Well, that's some drawings for people who keep track. Yeah, so these things are actually compressors that are used for our cryo coolers. So those are the bits that we keep cold, not with liquid helium, but with a closed circuit of helium. There is helium inside them, but they basically come with their own fridge. The cooling power is not so much, so you can get as cold as long as your object is not too big, and of course well insulated. And then you see here this is the radioactive source where we have the sodium inside. Okay, and now technically I don't have to lead you out because since this is virtual, you don't have to go out, but just to make it pedagogical, we will walk out again and up the stairs. I don't know if there were any more questions to this that has passed up. Else I guess I will stay here at the experiment. So, and then I will have a look for the questions.
There were a few more questions, Niels, but they didn't seem to be needing answering immediately.
Okay.
So I'll leave those to you.
So we'll go through here. I'll just start from the top again. I have seen that birds can use quantum mechanics for navigation and can do this without the extreme low temperatures. Is there any chance that antimatter could be created within living organisms for very short periods of time? Well, technically, positrons are created all over the place, like for instance, in kalium, which is in bananas. That means like a banana emits like a positron a day or a second or something. I've forgotten the exact numbers. So positrons certainly appear naturally, but of course they don't live very long because they very quickly meet some electrons. Now, one use of this is in fact in something called PET, positron emission tomography, which I actually had a picture of somewhere, but okay. Which uses a positron source like the one we have, for instance, or another one that you inject, typically short-lived ones, very short-lived ones that you inject in a patient. It emits positrons, and then you've made it so that the radioactive source molecules, they somehow stick to whatever it is you're interested in. It could be, for instance, the red blood cells, and then you can track oxygen consumption in the body, and you use this to track tumors, for instance. Okay, so positrons are definitely usable in and common in everyday life in that sense. By the way, this tour is freely available if you go on the link that you can see. So you can go around and find places you can ask questions if you want. Is there any difference in the mass between matter and antimatter? Is an electron heavier than a positron? As far as we know, no, there is no difference. That's what we're trying to find out. Essentially, I guess it's unlikely that the mass, at least, well, the mass could be different, but so far we've only measured the mass. The mass is difficult to measure, so it's only been measured with about 9 decimal places at this point, if I remember correctly. Okay. I heard work is on the way to upgrade the luminosity of the Large Hadron Collider. What does this mean, and what will it improve about the collider? The luminosity is essentially a measure of how many collisions you get per unit time. Okay, so what it will do is that there will be many more collisions. I've forgotten how many factors it will go up, but the collisions will be at the same energy as before, but added collisions means increased number of rare events and increased statistics on the events you already have, because there will be more of them. Okay, so it increases the statistics, and that allows you both to see things better and possibly to see things you couldn't see before because they just weren't happening often enough that you could see them in any significant way. Okay, so it will certainly increase its discovery potential. And they certainly hope that this will allow to see something that hasn't been seen yet. So can you remind me what was the LHC created for if the first 2 rings suffers for antiproton research? So the LHC was created to discover particles basically beyond the standard model. Well, the primary purpose was to discover the Higgs, which it did in 2012, if I'm not mistaken. Something like that. I'm not good with years. The years go by quickly as you age. And to discover new physics beyond standard model. Now, I've mentioned briefly that the standard model is not finished. I'm not sure if Prem came onto that yesterday, but there are a number of items that are not covered by the standard model, and people are pretty convinced that the standard model is essentially an approximation to some other model, which could be string theory at some level, but people don't know, and so far there are not enough clues for anyone to consolidate into any of the models that we have that have been proposed, or for that matter, propose something completely different. So that's what the LHC was for. Thoughts on the anti-periodic table? I guess the question here is whether we can make anything further than antihydrogen. the short answer is no. The slightly longer answer is that it is up to nature what the probability is to make a given particle, right? It's basically, that's what nature gives us. So as I said, you need 1 million protons on target to make one antiproton. And while the only knob we can turn on is essentially what are we shooting at, could be another proton, and with how much energy, could be the LHC. Now, if we turn up the energy, it becomes more difficult because we have to then stop them, again, to make atoms out of them. So turning up the energy is certainly not easy, but possible. But the fundamental problem is that turning up the energy doesn't give you that much. You will maybe gain a factor of 5 to 10 in the number of antiprotons, and then it flattens out and you get no more, because there's so many other things that are possible. Because as you turn up the energy, you can also make particles that are more massive, and other particles or other processes get more and more likely. That's exactly why the LHC has gone to such a high energy, to make more processes that weren't visible before likely. And they're all competing, if you want, or there are all different options. And that means eventually you don't really make any more antiprotons. And then the next step is, how likely is it to make something heavier than an antiproton? Because you have to make it in one go. We can't sort of make an antineutron and stick it onto an antiproton. You have to make the whole thing in one go, like an antihelium nucleus, for instance. And just to make an antideuteron, which seems like the most, okay, that's not really antiperiodic table much. It's just an isotope, if you want. So you could start with the simple thing of making an antideuteron. And just doing that, if you tried at the AD, technically the AD is already making antideuterons, but we calculated it recently, and it makes maybe around a few hundred per shot. Okay, so this few hundred you would then have to be able to capture and bring down. Now, if we actually had a few hundred deuterons in our trap, we could certainly detect them and work with them. But building the accelerator that can decelerate 100 particles, that's probably impossible. So you need more particles. The only way you can get more is by turning up the energy, which sort of equalizes this. And then you run into the problem is that you need to build a bigger decelerator to actually decelerate it. Anti-deuterons have been made, anti-tritium nuclei have been made, and anti-alpha particles have been made. But we are talking like maybe a couple of hands of anti-helium nuclei, anti-alpha particles, and they've been made at very, very high energies. So there is no chance we ever get to making anti-helium. I think it's the short answer for that. And even anti-deuterium is highly unlikely. It would require a massive investment. It is not impossible though, but require a massive investment. It's not obvious that it's impossible, didn't put it like that. Does charge time parity violation relate to the antimatter asymmetry? Yes. Technically, antimatter is matter after applying the charge time and parity symmetry. So CPT symmetry is what changes antimatter into matter effectively, if that answers that question. That's sort of a mathematical answer to that. Could you tell us more about your work at CERN? What exactly do you specialize in? So you've seen a lot of details here. I can give one example. I made the system that controls these power supplies so that they don't keep powering the magnet if the magnet becomes normal conducting because it burns it out. That's one of the things I've done. I have built some of these cylinders you saw. In fact, the ones on the picture I have designed and constructed. I didn't machine them myself, but I designed them and assembled the structures first. So the bits that I built sit over here somewhere. It's been rebuilt since by people of mine. We run the experiment ourselves. In fact, we do pretty much everything ourselves. Right now, I'm running an experiment that is supposed to use laser-cooled ions, that uses laser-cooled ions to indirectly cool the positrons. Because as I said in the presentation earlier, we have about 20 atoms per 4 minutes, which is amazing. But we will, of course, always like more. We are greedy because more particles means we can do more precise. In that sense, it's sort of similar to the LHC that I just talked about. And if we can cool the positrons colder than they already are, we can make more antihydrogen. It turns out, for various technical reasons, that the positrons are the more important thing right now. So I've been running an experiment to do that last year when CERN was otherwise shut down. So we managed to do that. That's an example of what I do. So it's a mix between electronics, mechanics, programming, analysis, and data taking. So we do pretty much everything ourselves. You mentioned that the spin of the particles in an atom led to it being magnetic. I have also seen that the electrons can exist in spin up and spin down states within the atom. Is this the same phenomena, or are they describing different things? Yes, that is the same phenomena. In fact, spin up and spin down is relevant here because we can only trap one spin state of the atoms. So an atom can be created. In fact, atoms, antiatoms, in the way we create them from scratch, they're created randomly in either spin up or spin down states. And now I have to think about whether it's only spin up or spin down we can trap, but it's only the one of them, because one of them is what's called diamagnetic, the other one is paramagnetic, and in a magnetic minimum, you can only capture diamagnetic things, not paramagnetic things. So a paramagnet is, for instance, a bar magnet. And if you think about it a little bit, you can't trap that in a magnetic minimum because it will turn around and become, okay, anyway, but yes, it's related. I probably screwed some signs up there on the spur of the moment here. I can't guarantee that. Does all normal matter turn into antimatter when energy is absorbed then? No. I'm not sure what that means exactly. Like, for instance, if you just shoot photons at an atom, it just destroys the atom. Okay, it could, if you think about absorbed. Okay, well, if you're sort of thinking, the energy is not technically absorbed. If I shoot protons on the target, as we do here to make antimatter, most of the energy goes, in fact, into heating the target. It gets incredibly hot. And a lot of it goes in to make the target atoms unstable. So they start decaying and become radioactive. So the target is quite radioactive. So most of the energy goes to all kinds of mundane things that have nothing to do with antimatter, if you want. Then there's a nice joke here. Does my auntie matter? Well, I can't tell. I don't know your auntie. Would you ever make antihelium? I think I answered that effectively. You explained how you go about creating antihydrogen. Okay, and how difficult would it be to create a larger? Okay, I think I've explained that. I think if we actually were given some amount, at least a measurable amount of antideutrons or anti-alphas, we could definitely, well, we could certainly make antideuterium. Antihelium is another can of worms because you need 2 positrons. So I'm not going to even. Quantum loops theory of string theory. I'm not a theoretician. I'm not even going to try to comment on that one. Are your experiments environmentally friendly, meaning in the energy you use and the equipment? Well, that's a good question. That's basically about whether CERN is environmentally friendly. I think technically any energy you use is only environmentally friendly if you use a renewable energy source. So the answer is, I don't know CERN's fraction of renewable energy use. But of course, then you would have to go through and measure every single supplier of equipment to CERN to figure out how green they are. I think that would be an insurmountable task, but not necessarily irrelevant. But I can't answer that. I'm guessing probably not in that sense. But we're certainly not polluting directly the environment in that sense in any way. With our experiments. For everyone who's still in high school, there's the opportunity to do a high school student internship program at CERN for 2 weeks. That is true. That's worth mentioning, where you're able to see many of the experiments and have a lot of interesting talks and more. Now, that's of course closed right now this year. If you end up at university, CERN has summer student programs that requires you to have done 2 years of research. So that's for the summer, and normally we would have had this summer, and we normally have some in our experiment. But this year it's not possible because of COVID-19. But there are lots of opportunities, and you should just go on the CERN website and check what opportunities are. Have anyone, in fact, also in Swansea internally, we have summer placements internally in the experiments in Swansea. Now we're talking about, I think James can maybe add to that, how that works.
Yeah, so I'm not so sure about the summer placements, but what I do know is that we have the, on the master's track, if you are studying for an integrated master's degree, then as part of that, we have a full-time semester-long research project. The majority of those are in research labs in Swansea, but there are, I believe, 2 spaces for people to work on your experiment. Niels?
Yes, that's right.
Yes, so residential at CERN in Geneva. These are reasonably, not everyone wants to do it. Some people want to stay in Swansea, but more than 2 people want to do it, and these are selected based on grades.
Yeah, I think yeah, okay. So we'll stick to that. Have anyone ever found a definite answer for how many cables are exposed in the hall? No. Well, I don't know if you're referring to our hall, else this is something I don't know about. Why does the door back there say agony? Yeah, that's because that used to be the cupboard where we kept all the chemicals in. Now they're kept in a safer place, as you might imagine. How do you get the particles to turn a quick 90 degrees as in go up the vertical cylinders? That is complicated. There's a lot of magnetic fields and a lot of simulations that went into that work by a Manchester PhD student. And it's not so difficult for positrons because they have low mass, so they just follow field lines in a nice and clean way. So as long as you have a magnetic field line goes around the corner, they will just follow. It is more complicated for antiprotons, but basically it requires simulations and figuring out. That's why there were so many funny magnets on that thing, is to actually make exactly the right field, because they tend to drift off field lines when they're heavier. The link for the tour is hard to see. May it be emailed to everyone after the talk? Yes, absolutely. It is part of the talk that I can put up. I think James had a place where you could put it. I'll put the talk up as a PDF file, so the videos won't work. But the links on the last page, the page where you have the overview, will work. Is that right, James? You have a place I can put the PDF file, right?
Yes, we will. We haven't done this format before, so we are learning as we go, but the intention is to make this material available. I will certainly email out a link to the tour that Niels is showing.
What is the 3.5 keV line and how does it link to dark matter? Oh, this I don't know what that refers to. 3.5 keV is really low, so I don't know if we have anything that's that low.
This was an astronomical observation, I believe, X-ray astronomy. I think that was resolved and not dark matter. It was only relatively speculative that it could have been dark matter, I think.
Okay, I see. Some astronomical source. Yeah, okay, no, okay. Could strangeless exist? Okay, now I need a particle physicist here. There's nobody alive. I think theoretically they could exist, but I think that was what triggered this craziness. But I think they concluded that since they don't, I think part of the answer to that is that the strong force is, actually Simon could answer this. He's working on the strong force. The strong force is so hard to calculate on that any predictions it makes like that are really stretching the imagination. And someone stretched the imagination at some point and thought that strangelets might exist. Then someone else, then they had an argument. There is a long argument you can find if you Google a little bit, that the features that strangelets then had, if they did exist, were such that you could exclude them on astronomical evidence that it would have actually collapsed lots of stars, if I remember correctly, and you could at least make the probability of them existing very, very, very low. I think that's the best I can answer that. And then a last question here, what programming language do you use? Well, we use LabVIEW a lot, which is a graphical programming language. And then we use Root and C++ and C, and for some analysis, people use Python and MATLAB, which is also a specific programming language, and Mathematica, which I guess you could call a language. But LabVIEW is running most of the experiment, is used for running most of the experiment, and Root is used for the key data acquisition software. And there's a Root is sort of a C-like interpreted language that has a lot of data analysis packages included in it. So it's generally used in particle physics for data analysis. I think that was the last question. Oh, it still says there's open 43. How is this possible?
I think that's just us not knowing how to use the Q&A properly to close them. I think
I have to write done. I don't have to write answered.
I don't think it matters. I think you have answered them.
Okay, I have gone to the bottom at least. Okay.
Fabulous.
Okay, well, I'll stop sharing this because people probably get dizzy by this turning. Okay, I think that concludes. There are no more last-minute questions here.
In that case, thank you very much, Niels. That is the end of our short series of webinars. I will follow this up with an email with some links that people have asked about. We will probably be doing more material. We haven't planned that yet. There is something in the works. I'll let people know about that through email. So thank you very much. I hope it's been useful. As ever, if you have further questions, you have my contact details. Please feel free to get in touch.
Yes, thank you very much for participating.
Okay. Goodbye.
Bye.